Hey y'all, welcome to section 8.2, Properties of Logarithms Solving. It's going to be a short one today because I took 8.2 and I split it up into 2 different days. Tomorrow's going to be the normal length. I just wanted to talk about solving. Remember, logarithms find the exponent, and what we've done before is, in order to solve these kinds of equations, we've had to rearrange them into exponential equations. So solving a log equation is super difficult. But if you rearrange it like this, base in the basement is 15, and then exponent is all by itself is 2. That's 15 squared is equal to x. So therefore, you can say that x is equal to 225. Rearranging this, we get x to the fourth is equal to 625, and then x equals 5. Log base 3 of 127, let's turn that into a logarithmic equation by just writing equals x, and then now that it's a logarithmic equation, you can turn it into an exponential equation. Base in the basement 3, exponent all by itself, x, and then equals 1/27. Well, 3 times itself 3 times is 27, so 3 to the negative 3 must be the reciprocal, 1/27. And just one more thing that I want to say as review is that if you take the log of a negative number, like log of negative 3, you're going to get an error. The domain of the log function is only positive numbers from 0 to infinity, not including 0. So, with that all said, here's what we're looking at. Log base 4 of x is equal to 5 halves. Now remember, you can change this to an exponent. The technique is the same. Change it to an exponential equation from a log. The exponent is by itself. The base in the basement is 4. 4 to the 5 halves is equal to x. And now there's kind of 3 different ways of solving this thing. You can look at it 3 different ways. You can solve it. You can say that the 2 is the square root, because it's in the denominator. 2 is what kind of square root is this? It's a square root. What kind of radical is a square root? And so therefore, you can have the square root of 4 and then raised to the 5th power, which is 5. And I think this is my favorite because the numbers stay low. You take the square root of 4, it's 2, and 2 times itself 5 times is 32. But there's another equivalent way you could do it. If you want to take the high road, so to speak, you could say that there's a square root of 4 to the 5th. 4 times itself 5 times is 1024, but when you take its square root, it's 32. You might need a calculator for something like that. Whereas here, you don't need a calculator. If you choose to take the square root first, the numbers stay low. The numbers get high in this method. You can also think of 5 halves as 2.5 or 2.5. So then this would be 4 to the 2nd power times 4 to the 1/2. And so 4 squared is 16. 4 to the 1/2 is the square root, and it's 2. So 16 times 2 is 32, same number. All right, log base x of 100, and then if that equals negative 2, we're going to change that to an exponential equation. Exponent is all by itself, and the basement is x. X is negative 2 is equal to 1/100. Let's take the reciprocal of both sides, or let's raise both sides to the negative 1st power. So the reciprocals, 1/100 is to the negative 1 power is 100 because that's its reciprocal, and x to the negative 2 is positive 2 here. Taking the square root of both sides, we get x equal to plus or minus 10. As good Algebra 2 students and remembering Chapter 3, always have to plus or minus, because negative 10 does solve this equation right here. But if you check both answers, you put it back in the original, log base to negative 10 of 1/100, we actually don't really want to think about what a log base of negative 10 would look like. We're just going to take positive bases. So we're going to discard the negative 10 and just report as x is equal to positive 10. That's the only answer. Here, log base 5 of 2x squared minus 6, log base 5 of 4x. Well, look, the bases are the same. Log base 5, log base 5. So log base 5 of thing 1 is going to equal log base 5 of thing 2. So therefore, thing 1 has got to equal thing 2. We do our algebra quadratics factoring, dividing all the terms on both sides by a greatest common factor of 2. We get this, x squared minus 2x minus 3, split the middle, and we get x is equal to negative 1, or is x equal to 3. However, if you try and put negative 1 into this original, we get log base 5 of negative 4, and you can't actually find that. That's not possible to be evaluated. So we're going to discard this negative answer because it doesn't check in the original. X is equal to 3. Got to check the original. Got in this for these kinds of things, we're going to have to make sure we check our answers because we don't want to try and take the log of any negative numbers. Similarly here, log base 4 of thing 1 is equal to log base 4 of thing 2, so therefore thing 1 is equal to thing 2. And then set it equal to 0, divide all the terms of both sides by 2, and then we split the middle, and this is what we get. X is equal to 5, x equals negative 2. However, you try and put negative 2 in here, you get log base 4 of negative 12, which you can't do. It's not impossible. It doesn't make any sense. I'm not going to look at it. This is, so x equals 5 is what checks out. And so therefore you can figure out what's underneath the red dot right there. Before I talk about the big idea, I just wanted to say what was my favorite year of school when I was your age. Sophomore year was a lot of fun. Freshman year was a lot of fun. Junior year was great, but senior, nothing beats senior year. So many wonderful things happened senior year, and I'll talk about it more later. But why don't you tell me, if you're in 10th grade right now, tell me what was your favorite grade so far, grade 1 through grade 10, or kindergarten. Kindergarten was a lot of fun. But my favorite year was 12th grade, senior year. The big idea is to solve. We've got 2 different techniques. You can translate between exponential and logarithmic. Not a new technique, but it might look a little different. And then the second technique is set the input equal to each other. These are the inputs right here, the powers, equal to each other when the log bases are the same. Base 5, base 5. Base 4, base 4. So you can use this when the bases are the same. Take care, y'all. What? 6.5-minute video? You're welcome.